So we are getting that after the simulation good results. So you can, so this is minus 10 dB. You can see if any antenna designing, you can return loss, you can see minus 10 dB. So minus 10 dB below, we are getting good results here, that at minus 5.5 terahertz, at 7.2 terahertz, and 8.4 terahertz. So you can change your frequency range also, operating frequency, as you can change your particular antenna design as a 5 terahertz to 8.5 terahertz. If you are change that particular frequency range, and you can see the particular your designing antenna designs. For that purpose, go to the simulation. Here the operating frequency we are getting the 5 terahertz to up to 5.5 terahertz, minus 10 dB. For changing purpose, go to the frequency. Here minimum value you can give as 5 terahertz, and maximum frequency you can give as 9 also you can give. Because I am why I am giving this particular frequency. In this particular frequency, we are getting three bands. So another bands is another frequency range. We are not getting any results. So particular operating frequency goes to that 5 terahertz to 9 terahertz. That particular range you can give here. Just to change the ranges, minimum frequency and maximum frequency. Just change the frequency of the frequency ranges. Just click on the OK. It will be changed automatically. After that frequency range changed, again go to the simulation, setup solver, apply, and click on the start. Why I am changing this particular frequency range means, we are in this 5 to 9 terahertz frequency range, we are getting three bands. Another remaining frequency range, we are not getting any bands. So we neglect that range, and the particular 5 to 9 is our operating frequency for this particular antenna design. So that purpose I changed that particular ranges. And after the simulation, I will show to the operating frequency 5 to 9 terahertz how much bands are coming. In this bands, we are getting the axial ratio or not. We can see that further step after the simulations. I will explain to that how to we can see that particular bands are matching in axial ratio or not. The three bands, the first band is achieved at 5.5 terahertz. This is a very high bandwidth band. Almost in this band, we can see axial ratio is coming or not. So that axial ratio, how we can see, how can we can simulate, how to values we can give. All things I can explain further steps. So simulated is completed. Now you can see that results. So it is clearly visible now. What I can change the 5 to 9 terahertz, that operating frequencies came here. It is visible or not, sir? Nice, sir.
Visible, sir.
So the operating frequency we can change it as a 5 to 9. These three bands also we are getting here. We can see the minus 10 dB below at 5.5 terahertz, at 7.3 terahertz, at 8.3 terahertz. The three bands we are getting in this particular operating frequency. So our antenna design is getting good results in terahertz frequency, three bands. If you are any BTech peoples or MTech peoples are there, this particular design, this results you can go for the conference paper. We are getting good results with this particular today's hands-on session. So we can see the axial ratio, how we are getting the matched or not in this particular three bands. For that purpose, you can go to the home. No, go to the simulation. Here one option will be there, field monitor. Just click on the field monitor. Here the lot of option will be shown here. The E field, H field, far field, field sources. The in starting session, the my guide is asking the why we are not in choosing the E field, H field, far field, all things. So you can after the results, you can select the E field and magnetic field, far field, all things you can select. So we this is the also very long taking long time taking process. So now I will explain focus on axial ratio. We are getting on particular three bands or not. So the purpose, select the far field RCS. That option we can select. Here the specification frequency and transient broadband. Two option will be shown here. Just select the transient broadband. Just after that, first you can select the far field RCS. After the specification, you can remove the selecting between frequency to the change to the transient broadband. Just to apply and OK. Then the far field is applied here. Then remain. You can go to that simulation point of view. So just to apply and start. After the far field broadband applying, then you can remain again. You can simulate your antenna design because of you are given the far field to that your particular antenna design. After this far field broadband and simulation point of view, after that simulation, I will go to the further step. How to we can see axial ratio we are getting for this particular antenna. That also very important thing in every antenna designing. We are getting three bands. That three bands are matching or not matching, we can see in axial ratio. If in these three bands we are getting any axial ratio value below 3 dB, our antenna goes to the circular polarization. If you are not getting any below 3 dB in our particular band, that our antenna designing goes to the linear polarization antenna. So the simulation point after the far field simulation is over, we are getting these results. So now we can go to that how to we can see the axial ratio values we matched or not. For that purpose, go to the post processing result templates. Sir, it is visible or not, sir? That options axial ratios values.
Sir, visible, sir.
Okay, okay. So here the general results, the you can go to the far field result properties, 2D, 3D field results, far field and antenna properties, filter analysis, general 1D, optic S parameter, all things it will be shown here. Already we are simulated antenna design and also given the far field applied and simulated that far field also. That option it is shown here, the far field and antenna property. Click on that one, go to that. Here the lot of option will be shown here, the far field probe and far field results. We are already given far field and far field. After the given that applied the far field, we simulated the particular design also. So that far field result you can select here. After the selecting the far field result, it will be open. One option will be open as a back in this back's far field result. Directivity and constant phi is equal to 0. Already it is selected one. Just go to the click on the all settings. Sir, it is clearly visible or not? This is very important thing, sir.
Yes, sir, visible, sir. Visible.
So in this far field, after the selecting, go to the browse monitors. In browse monitor, what far fields we are given for particular frequency range. So in electric field and magnetic field for particular frequency, we can give the 5 to 9 terahertz, 5 terahertz, 5.5 terahertz, 6 terahertz, 6.5 terahertz. That far field you can give and you can select the E field and magnetic field. What we are selected in far field, that option will be shown here. For this antenna design purpose, I selected first that far field broadband. I changed that option in I shown already that far field broadband I selected, transient broadband I selected. That option it is shown here. Just to that click on the far field broadband and select. After selecting, just OK. Here also after the selecting the browse monitors, the frequency setting single frequency by time and broadband is asking. Just select the broadband and go to that evaluation range. polar and constant, and 3D polar constant theta single direction, all things it is shown here. Just select the single direction. Theta and phase variation is asking. So theta you can make it as a 90 degree. You can change the degrees here in phase 0 to 150 degrees. So how do we can change the phase angles with the constant theta value as a 90 degree? The phase angles we can change it as a different variation, 0 to 150 degrees phase angles you can change. The starting stage you can give as a phase angle 10 degrees, and plot mode you can give here gain IEEE, and the axis polarization option go and change here ABS axial ratio theta. The axial ratio we are seeing, so select the axial ratio. The another option don't change anything. After we are just in this one we are changing only browse monitors, broadband, and evaluation range. In this one we are changed single direction, theta as a 90 degrees, phase as a 10 degrees we are given here, and the plot mode gain IEEE, axial ratio axis as a axial ratio we are selected, and go to C and selected OK. After that OK, click on the OK button. In this general results, what we are selecting that will be shown here clearly. So you can see here gain IEEE theta 90 degrees, phase is 10 degrees, phase angle is 10 degrees, the single type single direction, far field results, all things. So theta is 90 degrees, phase you can change 10 to 150 degrees. That purpose that select the this option also you can select this one. Here the lot of option will be shown here: settings, delete, duplicate, evaluate. Just click on duplicate, it will be copy and pasted automatically shown here. So it is shown is another copied and pasted here. After duplicate creating duplicated file, just click on and go to the phase angle we can vary from 10 degrees to change to 10 degrees to 150 degrees. So click on that one. The first option we can give in 10 degrees for phase angle. Here you can give 20 degrees. Just click on OK. It will be added automatically here after the changing that particular phase angle. So phase angle 10 degrees and 20 degree also changed here. Then go for another duplicate file, and here you can change the another phase angle as 30 degrees. So 10 degrees variation you can see, up to 150 degrees variation you can see. At theta angle as a 90 degree, and phase you can change 10 to 150 degrees variation. You can see how to that axial ratio plots are matching to that our particular antenna designing is matched or not. We can see at this phase angle variations. So phase 30 degrees you can change here. Then go to select the phase angle is changed as a 30 degrees. Now you can remain, you can select the duplicate file and go to that one particular file. Here you can change as a 40 degrees. It will be added here 40 degrees. So up to same thing you can do 10 to 150 degrees. So I will up to 90 degrees I will 160 degrees I can show to this particular design point of view. After then you can go, you can change your phase angle variation 10 to 150 degrees. So we can see first after 60 degrees variations. After then we can increase up to 150 degrees. So after the 60 degrees variation, it will be so you can see 10 degrees, the theta is 90 degrees constant, phase 10 to 10, 20, 30, 40, 50, 60. This phase angles we are changed. So after that we can see up to 60 degrees we are getting results or not for this particular in this axial ratio in particular return loss bands we are matching the axial ratio below 3 dB or not, we can see. So after that, given that particular phase angles, just to click on the evaluate all, it will be evaluated at particular what we are given theta and phase angles. In this one, we can see how to that our design result, simulated results matching to that axial ratio bands or not. We can see particularly. Almost, I think that one at any band we can see particular band it will really matched. This is our antenna goes to the circularly polarization. If it is not matched, our antenna goes to the linear polarization. It is simulating evaluated now. Hello, sir. Nageshwara, sir.
Sir, yes, sir.
Sir, that after the this evaluation process,
Sir,
I will show to that how much gain we are achieved for this particular antenna. After then, the graph and properties how to use for these antennas, I will show, sir.
okay, sir. Sure, sir.
So after the evaluation process, you can see our actual results are matched with the axial ratio or not. You can see it is a time taking process. It is simulating now, evaluated. After this axial ratio, I will show to that how much gain we are achieved for this particular antenna. The axial ratio bands are not, if not matched, we can post go to the post processing and we can change the phase angles up to 150 degrees and also theta also you can change different variations. The 45 degrees and phase angles we can change. Lot of options will be there, but in simple way I explained how to the particular bands are matched or not. Simple way I take time I'm explaining. Theta is the 90 degree and phase angles we are changing from 10 to 150 degrees variations. If it is not come, you can go and change the phase angles and theta angles. This is a lot of option will is there for that bands matching for that particular antenna designing or designing our antenna designing. It is evaluated is time taking time is 3:34. So after then we can see that gain parameters, and after then another important aspect in antenna design in terahertz frequency by using of graphene material how to the actual output is tunability that I will show in today's session. Terahertz antenna in terahertz frequency the actual output what we are getting that actual output we can tunability we can show, but by using of the particular graphene material that thing how to we can simulate and how can we can see tunability, all things I can explain clearly. Is evaluated process is taking long process time. Before that I will show to that graphene material how can add on top of that particular antenna design. You can see with the graphene. The graphene results is showing here. So how can add the graphene material on top of that CD array? I will show. Can show the sample diagrams, sample figures. I can show. After that, you can see results. It is not there, but I will show to directly how to add the graphene material top of that CD array. So it is taking long. Okay, just 2-3 minutes. Wait, I will. Okay. So evaluated process is completed. Now we can see that mm, below option tables. Just click on that one. 1D results. Just click on the 1D results. So axial ratio below 3 dB. The band is matched or not. You can see here. So I think any band are matched or not. I can see here. The first band is covers from 5.13 to 5.9. 5.13 to the first band. Return loss 5.3 to 5.9. In this band, we are getting any acceleration values or not. We can see here 5.3 to 5.9. Below 3 dB, we are not getting any results at this band. So go to the second band. Here, second band operating band as a 7.1 to 7.4. This is the second band. In the second band, we are getting achieved or not. We can see 7.1 to 7.4. 7.1. In this also not getting. Anyway, we can see that angle variation we can change. The 7.1 to 7.4 is here coming, but the 7.4, 7.1 to 7.4. This the band is covered, but this is the 3 dB here. Within the band is there. One band is covered here. 7. Our band operating band is 7.1 to 7.4. But in this one, normally the angle variation is there. 7.4 is matched one band is here. Below 3 dB is matched here. You can see third band. Third band operating frequency 8.0 to 8.4. 8.0 to 8.4. So in this band we can see the two results. 8.0 to 8.4. Just we are getting at 7.4 is matching. This one band is circularly polarized. We can achieve. Remaining two bands are not matched. With this, we can change that. We can see the phase angles up to 150 degrees. It will be matched. Remaining two bands also. After you can see, go to the post processing and results and templates. Then you can change the 0 to that 60 to 150 degrees variation. You can change and see that remaining two bands will be comes. That two bands also getting good results. I think it will be matched. Here one band is matched here. So we are getting one band circularly polarization for this our particular antenna design. Sir, now it is clear, sir.
Yes, sir. Okay.
So now we can see that our particular antenna design gain how much we are achieved. We can see now. For gain purpose, we can select any gain angles. Go to the duplicate. Double click on that one. Here evaluation range. Just change a single direction to the 3D. The step size is increased 5. The theta angle automatically it will be changed. The theta and phase angles don't you can change here. The flat mode is gain. Axis and polarization you can select as ABS and click on the OK and just click on the evaluated the particular gain dimensions results. Just evaluate that thing. So you can see how much gain we are achieved for this particular antenna design. You can see in this particular evaluation process. So within the 3 band, 1 band is matched below 3 dB at 7.2 to 7.4. So our antenna design is circularly polarized at 1 band. Remaining 2 bands is the linear polarization, but we are not seeing that particular phase angles changed up to 150. After changing 150 degrees, almost I think that 2 bands also matched with our actual output. So any antenna designing in gigahertz or terahertz frequency can target any research or R&D circularly polarized or not AC. So you can see that our particular antenna designing gain is coming. So the actual operating range is 5 to 9. So the maximum here coming, you can see here the gain of that particular antenna is 6.3. This is also very much good gain results we are achieved for this particular antenna. So gain is we are achieving 6.3 at our operating frequency 5.5 to 9 terahertz. We are getting 6.3 dB. Sir, it is visible, sir, that particular gain.
Yes, sir. Visible.
So today's session we are getting good results as a 3 bands return loss with high bandwidth. First band at 5 terahertz. Second band is at 7.3 terahertz. And third band is at 8.3. With 3 bands and 1 band I shown to that particular band is matched with that 7.4 axial ratio. That 1 band is circular polarization, and also I shown that this particular gain also. The gain 6 dB, 6.3 dB, very good gain. The gain we are achieved here. So this good results are came today's hands-on session. We are seen, but we are up to S11 parameter. We seen the values. We are not seen that this acceleration values so gain results. Now I am seeing, but they are getting this design is getting good results. So now I will explain to that how to actual output we can tunability by using of the graphene material. So can I proceed, sir? That one.
Yes, sir.
Okay, sir. After that graphene material added, I will simulate and show the results, sir. After then, almost okay, sir. 10 minutes is left. Okay. For that purpose, on top of the this is the without graphene. So we can make it the design on with graphene. With graphene means we can on top of the CDRA we can keep the one graphene material with the same radiations with the same radiation with the CDRA. The same material you can add on top of that CDRA material. So that purpose, go to the modeling. Here give to that select the cylinder material. just escape button. In terahertz frequency, we can see by using of the graphene material with the actual output is tunability or not. All things we can see. The axial ratio also tunability or not, and gain properties, radiation efficient properties, all things we can see by using of that particular graphene materials. The chemical potential we can change to 0.12 up to 1 chemical potential. If you are designing terahertz frequency, if you are design that particular antenna design in gigahertz frequency, we can by using the particular diodes, tunability diodes, character diodes, all diodes. By using of that diodes, you can show your particular tunability in your results. In terahertz, normally we can graphene material we can use. So now I will explain to the how to graphene material by using in terahertz frequency. Already we seen that particular antenna is there. Just we are added the another graphene material top of that CDRA, and how we are getting the results or not. But before that, we can see actual our actual operating frequency bands ranges. So you can see operating band frequency already noted now, noted already. 7 point, the first band is 5.3 to 5.9. Second band is 7.1 to 7.4, and third band is 8.0 to 8.4. These three bands we can tune in this particular operating frequency. So go to the modeling. Home. Modeling. So after the select the cylinder, it will be open the dimensions value. So the name you can give as a graphene. The outer radius same what we are given to the DRA material, that radius values you can give here as a radius value 12, and the Z minimum Z minimum is you can give thickness of fitness plus thickness of substrate what you are given in starting position. The thickness values you can give here, and TDRA also. Just copy these things and paste here. In top of the DRA, we are make it graphene material. So that graphene we can add here. TGRA, thickness of graphene. So before that graphene material, we actually one process will be there. We can add the graphene material on our library, material library. For that purpose, go to the macros, go to the materials. So before doing this process, we can add that particular material in our material library. If you are not added, the particular graphene material, it is not added in that. It is not shown in one particular material library. So you can add a material library, material graphene material in material library. So go to the materials, create graphene material for optical communication. Just click on that one. Material name given as a graphene. The temperature you can give 293 to 300. The chemical potential 0.0 is there. You can vary from 0.0 to up to 0.1, 0.1 to 1 chemical potentials. So you can give 0.5 here. So it will be automatically added in that particular material library. If you are not added in this particular this step, it will be not shown anyway. The graphene material is not shown anyway in this CST2. Before that, adding graphene material, this particular material this process you can add in this material library. After then, you can come to the modeling, select the cylinder, just escape. We are design the graphene metal top of the DRA. After graphene, material name graphene. After radius 12, x center, y center, z minimum, z maximum. Here you can give TGRA, T graphene. Here graphene. So you can see here clearly graphene EPS and graphene metal added. So just to collect the graphene EPS, click on the preview. It will be asked the graphene thickness. The graphene thickness you can give as a 0.2 micrometer. Just preview, click on the OK. So you can see clearly the particular black material added on top of the CDRA. It is clearly visible now. Sir, it is visible or not?
Yes, sir. Visible, sir.
Okay, sir. Okay, sir. That graphene material added. Then we can see how to the results are coming achieved by using of this particular graphene material. We can see the responses of the results. Then go to the simulation. You can click on the top setup solver, apply, and start. So before we are seeing the results without graphene, after the simulation, this process we can see that tunability responses. What we are getting the actual results are tunability or not. We can see by using of the graphene material tab. Already, how to we can see add the graphene material on that material library, and how to we can add the graphene material on top of the CDRA. All things I shown now, but we can the simulation is going on, but we can the band actual output bands it is tunable or not. We can see after the simulation. So almost this time is left. 7 minutes are left. After then, you can see the all things. The what we are designing antenna, what antenna we are designing terrestrial frequency, what results we are getting today's session, S parameters, axial ratio, gain, and tunability of the particular result response. All things we can see. So simulation is going on. This will take the 2 to 3 minutes time. Almost the simulation is done. So we can see that a particular results is tunable or not. We can see now. Okay. It is going. Simulation is going on. So 1 minute. So all things are evaluated. It is a very time-taking process. This is a simple thing, but by doing the parametric analysis, by giving the far field results for electromagnetic field, will be take almost 2 to 3 hours time. Just simply that's why I'm not giving any far field results to the E field H field. Just I selected broadband. If I give into that electric field, magnetic field, will be the simulation. It will be take mostly 3 hours time. By using of far field E field option, electric field, magnetic field. If you are select and simulated the thing, that what's the electric modes and magnetic modes what we are getting for that particular antenna design, we can see by using of this electric field and magnetic fields. That thing also very important in antenna designing. Which modes are we are generating by using of our antenna design. That things also very important aspect in antenna designing. So this is the going simulation.
Sir, all these parametric analysis is similar to the other type of antennas, or it is any difference in there?
Sir, parametric analysis depending on materials, you are selecting of the materials and that selecting of designing of your feed structure and the slot already we are making on cross slot, sir. The cross slot thickness that width and length we can see, sir. The parametric analysis, the cross slot shaped we design, but we can change the another cross slot in parametric analysis. We can see that that response also. Basically, we can see that main thing in parametric analysis, material thickness and the change the materials what we are taking for the your antenna designing, and the microstrip the feed line design, the only we are taking in this design microstrip feed line as a rectangular, but different feed line options also there. The zigzag steped, the cross the feed in feed different structures also there. That also we can change in my parametric analysis. The main thing is in our design the substrate thickness and also CDRA thickness and the CDRA radiation, and also that change of the particular material selection materials. In our design, the substrate material I taking polymer lossy. Then you can see change the parametric analysis with the silicon dioxide. That also very important. In the CDRA, you can see the thickness of the DRA height and also the radiations of the particular DRA. These all aspects we can see, sir, in parametric analysis and see the responses, how we are getting the particular results or not. The sample already we done all things in parametric analysis. The actual what we are getting good result, that aspect values we are taking and design today's session, sir.
That actually generally most of the people do the patch antennas where they will do parametric analysis. The process is same for this antenna also.
Same thing, sir. Same thing that I will show, sir, how to we can do the parametric analysis. Only little bit option will be there.
Okay.
After the simulation, I will show, sir.
Okay.
Same thing you can use, sir. That patch antennas, this antennas, same thing we can use.
Okay. Okay. Because most of the people will do on the patch antennas.
Yes, sir. Yes, sir. That
Yes.
patch antenna, same thing will be do, sir. The parametric I will show, sir, after simulation.
Okay, sir. Okay, sir. Thank you.
It is going to simulate taking. Okay, the simulation is completed, sir. Now we can see the tunability is getting tunable, but with the two bands also tunable here. We are actually in normal results. We are getting that S11 starting from 5.3 to 5.9. You can tunability at first band you can see. The band is shifted to 5.53 and close it to 5.7. The band is decreased here. At second band, it is starting from 7.1, but it is shifted to 7.3. The last band is closing at 8.4. Here coming the 8.6. So this is the tunability of that particular antenna results. The actual output, the little bit tunability we are shown here at first band, and that last band is two bands are combined, and that band is tunability at up to 8.6. Actual band we are covered 8.4, but it is shifted to 8.6. In first band, actual band we are getting at 5.3, but the band shifted to 5.4. So this is the after the tunability response of this graphene material. It is okay, sir?
It's okay. That means if you want to change the frequency range, we have to add the layers, no, sir? Is it correct?
Sir. So you can see graphene chemical potential we can change, sir. 0.1 to up to 1. On that aspects we can see that a particular graphene chemical potential. We can see different tunabilities also. That frequency also we can change.
Okay, sir.
By using it. So that last question we are asking that parametric analysis, sir. That I will show and I will complete the session, sir. So go to the home. Here the optimizer and parametric sweep option is there. Just click on the parametric sweep. Here click on the new sequence and click on the new parameter. Here you can see, sir, the name, the what the materials we are added in the particular antenna design. All options will be shown here. The L length of that particular material, slot length, slot width, thickness of the DRA, thickness of the feed, thickness of the ground, thickness of the graphene, thickness of the substrate, and the width of the particular material. These all options will be there. Select any one. So you can see, you can change the graphene chemical potential. Just select that one, and you can see the responses. You can change the graphene potential 0.1 to up to 1, and you can give the step width as given as the 0.1. So 0.1, 10 variations will be given. After click on the OK. So 10 linears, 0.1 to up to 1, 10 values it will be parametric analysis will be do. After then you can see the responses at 0.1 to how to is chemical potential working on graphene material, the tunability responses how to we can getting at 0.1, 0.2 up to 1 graphene up to 1 values. This is the how to do parametric analysis where we can see. So the almost to 4 point the time is 4 is there. So now I go to conclude my session. So today I designed that today's hands-on session is antenna design terahertz frequency. So bottom layer is microstrip field line we are design, and the two layers are designed here, the as it substrate layer and the top of the ground material layer. And we are in this design we are one cross slot we are make it here designing. On cross slot we are kept the CDRA. After this designing point, we are given the port excitation here at a microstrip field line, particular port excitation. So you can see here the port we are making it here at microstrip field line. After the port excitation, we go for the simulation for this particular antenna. After the simulation, we are getting the good results. We are achieved the good results in S11 at operating frequency 5 to 9 terahertz. 3 bands we are achieved at 5.3 to 5.9 first band. Second band is 7.4 to 8, 7.5. and the third band at 8.0 to 8.4. These are the bands were achieved, and also we can see that the particular bands matched at axial ratio or not. We have seen that post processing the theta angle is 90, the phase angle variation we can change it to the 0 to 150 degrees. So one band is matched I shown, and also how much gain we are achieved for this particular antenna, that also I shown almost 6.3 dB we are achieving this particular antenna design. And after this completion of the all aspects, we are going to that final stage, graphene material added on top of the CDRA, and actual output is the tunable or not we are seeing after the graphene material. I added a graphene material, how to we can add a particular graphene material before the given that graphene material. So after the graphene material, we can see the frequency responses also. The one band is also shifted, and also another band also shifted here. So we can, with the graphene material, the actual return loss, and we can see the tunability and axial ratios response and gain parameter response and radiation efficiency response. We can see all things we can see after the graphene materials added after the simulation point of view. So, okay, this is today's hands-on session. We are getting good results, and thank you for giving good opportunity to my supervisor for taking given this hands-on session. And if you have any doubts, just contact me or contact to my supervisor. The mail ID amarjitk@nitw.ac.in. If you have any doubts or personally, you can take the number from that. Our senior is also here there, Nageshwar Rao sir. He's also done PhD and is my senior. Thank you, sir, for seeing here.
Thank you, Jacob. Good session we have today.
Okay,
Actually,
sir.
most of the people will do, if anyone is doing on the different type of antennas, then it will be the added for them.
Yes, sir. Yes, sir.
The session is also very clear. Thank
Okay,
you very
sir.
much.
Thank you, sir. Thank you, sir, for seeing to you here. And if you, sir, if you personally, if you ask any contacts, you can give, sir, particular.
Okay,
If
sir.
you-
I will give.
if you candidates, if you have any doubts, that's directly contact to our supervisor Amarjit sir. The Gmail ID is amarjitk@nitw.ac.in. If you have any doubts, directly contact to the personal contact is there with my senior Nageshwar Rao sir. Thank you, sir. Thank you for giving good opportunity for hands-on session, sir. Okay, sir. Can I conclude this and stop the sharing this one?
Yes, sir. Yes. Madam,
Okay, thank you. Thank you, sir.
Thank you, ma'am. Thank you, ma'am.
Thank you. Nageshwarrao,
hello, madam.
అది కొంచెం అది వ్యాలిడిక్టరీది చేస్తారా? కొంచెం
చేస్తాను మేడం.
వ్యాలిడిక్టరీ చేస్తే రేపు ఇచ్చేద్దాము, రేపు డిస్ట్రిబ్యూట్ చేద్దాము. మీరు వీసీని పిలుస్తానంటే పిలవండి.
ఓకే మేడం.
మీ ఇష్టం అది.
ఓకే మేడం. ఓకే.
వ్యాలిడిక్టరీ ఒకటి చేయాలి, రేపు ఫీడ్బ్యాక్ది చూడాలి, ప్లస్ క్వశ్చన్స్ కూడా ప్రిపేర్ చేయాలి కదా వాళ్ళకి.
మేడం విల్ డూ. క్వశ్చన్స్ ఆల్రెడీ ప్రిపేర్ చేశాను.
క్వశ్చన్స్ మీరు చేశారు, అది ఫీడ్బ్యాక్ నేను మీకు పంపించాను మెయిల్లో. రేపు వీళ్ళ దగ్గర నుంచి ఫీడ్బ్యాక్ తీసుకోవాలి.
ఓకే మేడం.
ఇంకేం చేయాలి? వ్యాలిడిక్టరీదే కదా ఇప్పుడు రిమైనింగ్. ఇంకేమైనా చేయాలా నేను?
ఓకే మేడం, అన్నీ అయిపోయినట్టే.
అటెండెన్స్ మీరు తీసుకుంటున్నారు కదా వీళ్ళ దగ్గర నుంచి?
తీసుకుంటున్నాం మేడం.
సరేనండి, అయితే సరే. ఇక ఇది నేను ఇదే సెషన్ క్లోజ్ చేసేదా?
ఓకే మేడం, చేయండి మేడం.
రేపు 10 కండి. నేను ఆ ఎఫ్డిపి లెక్చర్ షెడ్యూల్లో అది 11 to 12 అని పెట్టాను, కిరణ్ కుమార్ గారిది. అది రేపు 10 కండి లెక్చర్ సెషన్. పార్టిసిపెంట్స్ టుమారో లెక్చర్ సెషన్ ఈస్ దేర్ ఫ్రమ్ 10 o'clock, not from 11. Please join the Google Meet at 10 o'clock, not at 11. Please join the Google Meet at 10 o'clock, participants, if you are listening. Okay, నాగేశ్వరరావు నేను వెళ్ళిపోతున్నానండి.
ఓకే మేడం.
సరేనండి.
ఇంగ్లీష్లో అందుకు అడిగారు అంటే మీరు ఫోర్త్ ఫస్ట్ ఇయర్ ఫైనల్ ఇయర్ ఏం తప్పదాకా ఏం చేస్తానని అడిగారు అనుకున్నాను. అదే అంటే నేను చూసినప్పుడు ఎక్కడ దాకా చెప్తామని అనుకుంటున్నాను. మా ఇంట్లో చెప్తామని అదే అంటే దాని 2 డేస్లో మీరు ఎక్కడ కంప్లీట్ చేస్తున్నారో చెప్పాలి అని అన్నారు. రేపు వస్తున్నాను అందుకే ఈరోజు చెప్తామని చెప్తా అక్కడ ఉన్నారు మా ఆయనకి చెప్పాలి. సరే ఏం చేస్తారో ఒక నిమిషం నేను వింటాను కూర్చో నేను నోట్ చేసింది మేడం చెప్తాను. క్లాస్కి వెళ్ళారమ్మా ట్రైన్ నుంచి వెళ్ళారమ్మా నాకు తెలియదు
Nice. Fine. Once come here now, WhatsApp. Where? Yes, okay. How much percentage did you get in 3 to 2? 9.55. 9.55. CGPA 9.55. Yes. Is it improved? Only 2 and gone. Okay. I was satisfied. Okay, no problem. In third year, you'll get better percentage. వర్క్ చేసుకుంటున్నా కొంచెం డిస్టర్బ్ అయింది.
అదే అప్పుడు ఫస్ట్ ఇయర్ చెప్పాను
ఏంది అసలు మీ ప్రెజెంటేషన్ నేను వెళ్ళలేదు అసలు ఫస్ట్
నేను లాస్ట్లో అయితే యాక్చువల్లీ చెప్పాను ఫస్ట్ 2 ప్రాజెక్ట్స్ ఉంటున్నాం స్కిన్ క్యాన్సర్ డిటెక్షన్ అలా హెచ్ఆర్ చేద్దామని. సో ఫస్ట్ మేము ఏం జరిగిందంటే మాకు స్టార్టింగ్లో స్కిన్ క్యాన్సర్ డిటెక్షన్ అనుకున్నాము, చాలా చూసాము, అంటే పేపర్ చూసాము, ఏం దొరకలేదు చాలా రోజుల దాకా. తర్వాత మిడిల్ ఏమైపోయిందంటే
స్కిన్ క్యాన్సర్ డిటెక్షన్కి ఉంటాయి చాలా
అంటే పింక్ బోర్డ్ మీద లేవు.
అంటే మీకు పింక్ బోర్డ్ మీద ఉండవు, బట్ ఏంటంటే మీరు వెళ్ళ కోడ్ రాస్తారు అంటే సీనా సీలోనా పింక్ బోర్డ్
నేను మైనర్ పార్టీస్ కూడా అదే చేసాను, ఇమేజ్ క్లాసిఫికేషన్ పింక్ బోర్డ్ మీద చేసాను. మా ప్రాసెస్ ఏం ఎలా చేసామంటే ఫస్ట్ డీప్ లెర్నింగ్ వచ్చినాను. డీప్ లెర్నింగ్లో మేము పైథాన్ కోడ్ రాసాం దానికి సంబంధించింది. ఆ కోడ్ని YTCHLSలో కన్వర్ట్ చేసుకున్నాం వేరేలాగా. ఆ ఎక్స్పోర్ట్ చేసుకొని వేరేలో అదే మన వివాడలో పెట్టుకొని బిట్ స్ట్రీమ్ జనరేట్ చేసుకొని బ్లాక్ డయాగ్రామ్ వేసుకున్నాం. ఐపీ జనరేట్ చేసి బ్లాక్ డయాగ్రామ్ వేసాం. అదేంటంటే ఆ ఫైల్స్ అన్నీ మనకి ఆ పింక్ బోర్డ్ SD కార్డులో పెట్టుకొని ఫైనల్ కోడ్ ఉంటుంది కదా, ఆ కోడ్లో అవన్నీ యాడ్ చేసుకున్నాం, బిట్ స్ట్రీమ్ ఫైల్స్, వెయిట్ ఫైల్స్ అన్ని. సో మాకు అది వచ్చింది. సో ఈ స్కిన్ క్యాన్సర్ డిటెక్షన్ అయిపోయిందంటే ఫస్ట్ ఆఫ్ ఆల్ వాటికి పైథాన్ కోడ్ అనేది కొంచెం ఎక్కడ ఏమంటారు కొంచెం రిఫరెన్స్ ఏం దొరకట్లేదు. చూద్దాం
బేస్డ్ ఆన్ ప్రాసెస్ మీరు రాయాలి.
అదే దొరకదు. ఫస్ట్ కూడా నేనే రాసాను సీనియర్ కోడ్ కూడా యూడెంలో కోర్స్ తీసుకుని మరి నేర్చుకొని రాశాను. అది కాకపోతే ఈ మెలనోమా డిటెక్షన్ అనేది ఎంత చేసినా మన కోడ్ రాస్తే మోస్ట్లీ ఆ కోడ్తోని 20% 30% అక్యురసీ కంటే ఎక్కువ రాదు నాకు. అంటే సెలెక్టింగ్ స్కిన్ క్యాన్సర్ అంటే ఒక డిసీజ్ ఉంది, మెలనోమా అని ఒక డిసీజ్ ఉంది. సో దాన్ని ట్రై చేసాం.
మెలనోమా
మేము న్యూమోనియా అనుకున్నాం డిటెక్షన్, కానీ లాస్ట్ ఇయర్ సీనియర్స్ ఒకటి చేశారు మేము. అది పద్మసార్ మ్యామ్ స్టూడెంట్స్ వాళ్ళు కూడా వర్కౌట్ కాలేదు న్యూమోనియా డిటెక్షన్ వాళ్ళు. సో మేము వాళ్ళు ఏంటంటే FARతో చేశారు, సరే FFT ఫాస్ఫేట్ ట్రాన్స్ఫార్మ్ యూజ్ చేసి ఇంకా HCM యూజ్ చేసి చేశారు వాళ్ళు. అసలు వాళ్ళకి అది వర్కౌట్ అవ్వలేదు. మేము ఏమంటే సీరం ఇండస్ట్రీతో చేద్దాం అనుకున్నాం న్యూమోనియా. కాకపోతే వాళ్ళు అన్న వాళ్ళు ఏమన్నారంటే మేము ఆల్రెడీ చేసాం కాబట్టి మీకు ప్రాబ్లమ్ ఏంటి రివ్యూస్లో అలా చేయకూడదు ఇది అంటే, సో కొత్తగా చేద్దామని చెప్పేసి హెచ్ఆర్ స్కిన్ డిటెక్షన్ అనుకున్నాం. ఇది స్కిన్ డిటెక్షన్ ఎంతవరకు చూసేసరికి అవ్వలేదు మేము. మధ్యలో ఈ పేపర్స్ మైనర్ పేపర్ కొంచెం వర్క్ ఉండేసరికి ఎక్కువ చూడలేదు. తర్వాత ఈ హెచ్ఆర్ చూసాము. సో మేము ఈ రివ్యూ వల్ల కన్నా మీరు చెప్పారు కదా మెయిల్ అని ఆ బిట్ స్ట్రీమ్ దాకా జనరేట్ చేసి బ్లాక్ డయాగ్రామ్ దాకా చేద్దామని ఈ రివ్యూ దాకా అనుకున్నాము. మేము జస్ట్ డేటా సెట్స్ అన్ని చూసాను. ఇంకా యూడిక్యార్ సంథింగ్ డేటా సెట్స్ ఉన్నాయి, 3 డేటా సెట్స్ ఉన్నాయి నార్మల్ హ్యూమన్ ఐడెంటిటీ రికగ్నిషన్ డేటా సెట్స్. మేము దానికి కోడ్ ట్రై చేసి దాన్ని మేము HLSలో వెరిలాగా కన్వర్ట్ చేసి బిట్ స్ట్రీమ్ బ్లాక్ డయాగ్రామ్ దాకా చేస్తాం మేము ఈ రివ్యూ దాకా. సో అదే చెప్తాము. ఇది ఫస్ట్ ఫేజ్ రివ్యూ కాదు, నార్మల్ వెరిలాగ్ దాకా అంతా కంప్లీట్ చేసుకొని
ఒక పేపర్ మీద రాసేవాము ఆరంభిస్తాము. యాక్చువల్గా క్యాన్సర్ డిటెక్షన్ ఇస్ ఏంటంటే చాలా రీసెర్చ్ అవుతుంది.
అదే
ఓకేనా, అంటే వేరియస్ పార్ట్స్ మీకు స్కిన్ క్యాన్సర్ డిటెక్షన్ మీద కూడా పేపర్స్ దొరుకుతాయి. అంటే ఎలా అంటే మీకు ఈ మీ డిటెక్షన్ ప్రాసెస్కి న్యూరల్ నెట్వర్క్ ఎలా వర్క్ అవుతుంది, ఓకే, అది ప్రాసెస్ మీరు అండర్స్టాండ్ చేసుకుని బేస్డ్ ఆన్ దట్ అల్గోరిథం యూ హావ్ టు రైట్ వెరిలాగ్ కోడ్.
అంటే వెరిలాగ్ కోడ్ ఫస్ట్ ఆఫ్ ఆల్ మనం డైరెక్ట్గా వాటికి రాయలేదు అన్నమాట.
ఓకే పైథాన్
పైథాన్ మేము చూసాం స్కిల్ డిటెక్షన్కి. కాకపోతే మాకు అక్యురేట్ కోడే మాకు చేయడానికి రావట్లేదు. అదేమవుతుందంటే ఎంత చూసినా మనకి వెరగా కన్వర్ట్ చేస్తున్నాం. చేసినప్పుడు మ్యాక్సిమం ఎర్రర్స్ వస్తున్నాయి దాంట్లో, అసలు చాలా ప్రాబ్లం అవుతుంది. ఆ ఐపీ కూడా జనరేట్ అవ్వట్లేదు. సో ఇంకోటి ఏమవుతుందంటే మనకి పింక్ బోర్డులు అనేది ఎక్కువ మెమరీ పెడతాం అనుకోని అది కూడా మన ఫస్ట్ టెన్సర్లో రావట్లేదండి. పింక్ బోర్డులో మన దగ్గర ఉన్న పింక్ సెట్లు టెన్సర్స్లో రావట్లేదు. మనం మాక్సిమం ఈ స్కిన్ డిటెక్షన్, న్యూమోనియా, ఈ హెచ్ఆర్ కూడా టెన్సర్లో పక్క అవసరం. మేము మైనర్ చేసినప్పుడు టెన్సర్లో అసలు డౌన్లోడ్ అవ్వట్లేదు ఆ పింక్ బోర్డులో. మాకు అది మేజర్ ప్రాబ్లం అవుతుంది. ఇప్పుడు కూడా ఒకసారి మళ్ళీ ట్రై చేయాలి, వస్తుందో అని కూడా అర్థం కావట్లేదు. మేము మైనర్ చేసినప్పుడే షెబెల్ సార్ అడిగితే అది రాదమ్మా టెన్సర్స్లో రాదు, మన బోర్డ్స్లో పింక్ బోర్డులో అయితే రాదు అని అన్నాడు సార్. సో అదే ప్రాబ్లం అవుతుంది. న్యూమోనియా రీడ్ చేయాలన్నా టెన్సర్స్లో కావాలి. ఇప్పుడు హెచ్ఆర్ కూడా 100% టెన్సర్స్లో కావాలి. రియల్ టైం డిటెక్షన్ కాబట్టి 100% టెన్సర్స్లో కావాలి. సో ఫర్దర్ ఏమన్నా మాకు ఏమన్నా దొరికితే చూస్తాం అన్నమాట. మాకు ఈ స్కిన్ డిటెక్షన్ చాలా టైం, అంటే యాక్చువల్లీ ఎలా చేయాలో దాన్ని చూసి టైం చాలా తీసుకుంది. ఒకవేళ దొరికితేనేమో మెలనోమా డిటెక్షన్ ఎస్పీజీ చేసినది ఉంది. అప్పుడే 2016 పేపర్ వాడు ఇట్లనే ఎస్వీఎంని వాడి చేస్తున్నాం, సిఎన్ వేరు వాడలేదు. ఒకవేళ నార్మల్ సిఎన్ ఎన్ఎస్టీ చూస్తేనేమో అది పింక్ బోర్డ్ మీద మరి నార్మల్ కోర్స్ ఉంది. దాంట్లో కోర్స్ కూడా ఏం లేదు, మరి ఎలా చేసామో చెప్పారు అంతే. పేపర్లో కోర్స్ ఏం పెట్టలేదు వాళ్ళు. ఏంటి నార్మల్గా పేపర్లో ప్రాసెస్ చెప్తున్నారు. సో అది నార్మల్గా సిస్టమ్ ఈజీ చేయొచ్చు మేము. హార్డ్వేర్ యాక్సిలిటీ చేయాలంటే చాలా ప్రాబ్లం అవుతుంది. స్కిన్ డిటెక్షన్ మనకు నార్మల్గా సిస్టంలో మనం కోడ్ రన్ చేసి జూపిటర్లో రన్ చేస్తే మనం ఇన్పుట్ ఇమేజెస్ ఇస్తే ఈజీ డిటెక్ట్ చేస్తుంది. అదే మనం హార్డ్వేర్ యాక్సిలేటర్ చేసుకున్నప్పుడు అక్యురసీ తగ్గిపోతుంది. వెరిడాగ్ చేసినప్పుడు ఎర్రర్స్ కూడా చాలా వస్తుంది. నార్మల్ కోడ్తో చేస్తే సింపుల్ కోడ్ రన్ చేద్దామని
అందుకు కన్వర్షన్ యూజ్ చేసి చేస్తున్నాం. కన్వర్షన్ అందుకే కన్వర్ట్ చేసుకుని చేస్తుంటే యాక్యురేట్గా వస్తుందా?
ఫస్ట్ మేము మైనర్కి కన్వర్ట్ చేసుకొని చేసాము. 90s కన్వర్ట్ చేసుకొని చేసి దాంట్లో ఎర్రర్స్ వస్తేనే మేము ఇచ్చింది. అది నార్మల్ ఇమేజ్ ట్రాన్స్మిషన్ కాబట్టి అది ప్రాబ్లం ఏం రాలేదు. కాకపోతే ఇప్పుడు డిటెక్షన్ కాబట్టి ఆ పర్టికులర్ కొన్ని ఆల్గరిథమ్స్ దగ్గర ప్రాబ్లం అయిపోతుంది. అంటే హై ఎండ్ ఆల్గరిథం తీసుకోవాల్సి వస్తుంది. మేము జనరల్గా సిఎన్ఎన్ వాడింది యోలో V3 అవి వాడాము. దీంట్లో ఎలా అంటే ఆల్గరిథమ్స్ కూడా చాలా కాంప్లికేటెడ్ ఉంది. బాగా నార్మల్ రాస్బెరీ పై అయితే ఈజీ చేయొచ్చు. అది నార్మల్ మనకి పైథాన్ కూడా డైరెక్ట్ రన్ చేయొచ్చు. కానీ ఈ హార్డ్వేర్ యాక్సిలేటర్కి వచ్చేసరికి చాలా ప్రాబ్లం అవుతుంది. పెన్లా కూడా అక్యురేట్ లేకపోతే అది బ్లాక్ డయాగ్రామ్ జనరేట్ అవ్వట్లేదు, ప్లస్ డిజిటల్ కూడా రావట్లేదు. అదే హెచ్ఆర్ ఒకసారి మ్యాక్సిమం ఈ రివ్యూలో డెవలప్ దాకా ట్రై చేస్తున్నాం. డిజిటల్ జనరేట్ చేసేంత వరకు ఈ రివ్యూస్లో చూపిస్తుంది. అది చెప్తామని
టూ పాయింట్స్ నేను చేస్తాను పేపర్ మీద రాసి. మేడం వచ్చారేమో చూడు. రాసి నీ ప్రాజెక్ట్ నాకు పెద్ద తెలియదు కదా. సో నువ్వు చెప్పింది నేను ఇప్పుడు విన్నాను కానీ తర్వాత మర్చిపోతాను. తెచ్చుకో లేకుంటే ఇక్కడ
మార్నింగ్ 3-4 టైమ్స్ వచ్చింది మేడం.
ఇక్కడ
మళ్ళీ ప్రాజెక్ట్ రియల్ ఎస్టేట్ వాళ్ళు ఉంటారు అక్కడ అంటే
అదేంటది